Alright, let's go ahead and start. And then we give you a slide forecast for the part of the lecture tomorrow. So we'll be going over the midterm exam tomorrow. Okay, it's going to be in the second hour. Right? And what I'm showing here is the histogram of the midterm exam scores. You see quite a nice normal distribution there. And actually, to my surprise, given a very long exam, we still have students who did very well, receiving grades such as 80 points, 90 points. Okay. So we'll talk about the midterm grades tomorrow a bit more, but just to let you know that most of you falls, let me see, yeah, in the range between 50 to 70. Okay, and some did extremely well. Some might have a bit of trouble dealing with the Google form as a way to take exams. Alright, so we'll talk more tomorrow. And the topic for today. We're going to bring back the overview that we actually went through briefly last week, so that it gives you a very good picture of what's coming ahead most of the lecture this week. So part 1 is going to be the overview, running again. And then the packet format of TCP. Now, packet format of TCP is no longer trivial as UDPs. Do pay attention, because quiz is going to come up right after we introduce the packet format. And this is 3.5, connection-oriented transport, particularly the TCP protocol. So in this particular section, we're definitely going to talk about the RDT implemented in TCP. Now, provided the background, okay, very extensively in 3.4, you should be able to understand TCP's implementation of RDT, TCP's design of RDT. Now, in addition to the RDT in TCP, we are also going to talk about the packet format of TCP. And that is what the segment structure meant here by the textbook authors. And then there are two minor functions, but necessary functions in TCP. One is called the flow control. The other is called the connection management. And this is the overview. TCP we know already. Just like UDP, it's what? End-to-end process-process communication. So end-to-end there can also be referred to as point-to-point communication. We have a sender process and a receiver process. Now, in this connection here, what we're doing is to do reliable and in-order data transmission. Now, what's a little bit unusual when we talk about TCP is this. Instead of earlier, when we were talking about the general principles of RDT, we are counting the data by what? Packets. Packet 0, packet 1, packet 2, packet 3, so on and so forth. But in TCP, we count data alright, but we count the data by the bytes. Byte 0, byte 1, byte 2, and so on and so forth. So that connection here, when we are passing data around, we are actually passing a stream of these bytes. Right? So there's no more message boundaries, or there's no more packet to packet separation. Right? And last, this is actually telling you ahead of time that TCP's reliable data transfer is doing this, the pipeline-based RDT, so that we have a window size there where the size n is definitely larger than 2. And so we could have multiple packets in transit, so that the utilization of the connection there can be higher. Okay. Now, what we don't know quite yet is this window size is also used not just for reliable data transfer. Later on in section 3.6 and 3.7, you will also hear it's also for the congestion and flow control. Okay, so there's going to be a window size for flow control. And the window size for RDT is also used, okay, for congestion control. And conveniently, in flow control, what's being done is the receiver will every now and then tell the sender, hey, you might want to slow down or you might want to speed up depending on how much the buffer space is occupied at the receiver side. you see what happened at the receiver end of the TCP is this. Data will come in continuously from the sender. Data will be extracted and passed up to the application layer process. So there's an incoming rate and there's also an outgoing rate. When the outgoing rate is slow, incoming rate is fast, then you see the buffer space is quickly exhausted. Okay, so at that point, receiver tells the sender, hey guys, slow down. All right. Now, the other way around, if the buffer space is very empty, then telling the sender, feel free to send more. So flow control there. Okay, mainly allowing the receiver to tell the sender, hey, slow down or speed up, such that there's no congestion occurring at the receiver side. Because if the incoming rate is high, outgoing rate is slow, over time, when the buffer is exhausted, the incoming packet, incoming data will be what? Will be dropped. Okay, so delay long, and you see also data loss there, right there at the receiver. So this is to avoid also congestion, but it's a bit weird. It's actually to avoid congestion at the receiver side, not quite in the middle of the internet. Okay, so when I say in the middle of the internet, I actually meant congestion in the core of the internet. Sender process, receiver processes are what? At the end of the internet, at the edge of the internet. So flow control there is to try to control the end processes such that there's no packet drop at either end. Congestion control, on the other hand, is to control such that there's no packet drop or congestion in the middle, in the core of the internet. And TCP, being connection-oriented transport layer service, is sending some messages in the beginning before data can be transmitted. So there are some handshaking being done right before the data exchange. And these handshaking messages are there to set up the initial states of the sender and receiver. And that is called the connection management part of TCP. Last but not the least, there's a mindset change here in a TCP connection. Data traveling in a TCP connection is now full duplex. What I meant by that is the data flow is going, bidirectional. Okay, so two processes or point-to-points, will be sending data this way as well as this way. Now, why is this a major mindset change? If you recall in 3.4, when we were talking about these reliable data transfer mechanisms, we always say what? This is the sender side of RDT, and this is the receiver side of RDT. What we are saying there implicitly is also, this is data sender side of RDT. This is the data receiver side of the RDT. Data receiver there, receive data. It transmits something as well, but it's transmitting only what? The feedback messages, the ACK messages. The receiver there does not send data. So TCP here you see being more general. Data can go either way. So the two processes will be implementing both the sender and receiver finite state machines. And the last bit is this. MSS, a special term that is referring to this, the maximum segment size. If you recall, a packet at the transport layer is called a segment. So maximum segment size is essentially the maximum packet size. Okay. In reality, in actual TCP implementation, we're still sending data packet by packet. But the sequence number we'll be checking to do reliable data transfer is now counting the bytes of the data, not the packet numbers of the data. TCP segment structure, aka the packet format. It does look a bit complicated, definitely more complicated than the UDP packet. If you recall, in UDP we do have these fields: source port number, destination port number, as well as the checksum. So all these are what called the header fields. So in TCP packet, the header part is substantially larger. While the data part, it's still variable lengths that could be large, could be small. Oops, yeah. So the overall structure in TCP packet is actually very similar to UDP, two parts, header and data. The main difference is where? The header part. Okay. So some of the header fields repeat itself. We see source port number and destination port number as well as checksum also in TCP packet header. But what else in the UDP packet header that we don't have or we do have in TCP's packet header? And here's UDP's packet format. So we do see source port number, destination port number, checksum. And what else is in UDP's packet header? The length. So that is the entire packet size, including the header as well as the bytes in the segment. So data and header together, okay, in this field, the lengths. And do we have lengths here in TCP's packet header? Well, if we look around, yeah, something slightly similar. It is lengths. Okay, so LEN is actually short for length, but it's only the length of the packet header. So this part versus UDP's length, quite different. Semantic, very different. So UDP's length actually talk about the entire packet size, but length here is only covering the first part of the entire packet structure, the header length. Do we have lengths in TCP's packet header? We actually don't. The thing that we have the closest is this, the header length. So the length in TCP packet header counts only the size of the TCP packet header, while the length in UDP's packet header counts the entire UDP packet. Given that we're already talking about the header lengths, why don't we talk about these special bits, okay, special flags in the TCP packet header? First is the A flag. Okay, so this is called the ACK flag as well. When it's turned on, when the ACK flag is on, that's indicating that the acknowledgement number here is actually valid, meaning that the sender of this packet is trying to tell the receiver that it's trying to acknowledge certain bytes being received. Okay. And these three R, S, and F bits, they are there to indicate packets being used to do connection management. So for example, SYN here, the SYN packet is to set up connections. The FIN packet, which is Latin for the end, conveniently, okay, is to tear down a connection. RST, or the R bit here, means reset, that is to re-establish the connection, to re-initialize certain parameters between the sender and receiver of a TCP. And P bit, P stands for push, that is to push data now. So this is to actually pass the data out as soon as possible, but it's generally not used. Just like the U bit, this is urgent, so this is indicating that whatever data is here is urgent. So pass it out through the network or to the application layer as soon as possible. Okay, so you see urgent, the purpose, and push, somewhat similar. The ambition of the network engineers much early on is also that hopefully a data network or the internet can also allow urgent data being sent, just like we could make it 911 call, or in Taiwan 110 call to get police's attention or the fire department's attention as quick as possible. But unfortunately, the way the internet is designed is just not very good for urgent critical data transmission. And we said that these are not used, so there are a number of bits not being used. But the fact is actually there are two more bits being used. It's called the C bit and the E bit. Now these two bits are not really for reliable data transfer service, not for connection management purpose. They're actually there for congestion control. Okay, but it's not quite the congestion control implemented in TCP though. Okay, it's just that the engineers are expecting, okay, later on TCP's congestion control can be extended, okay, together with the core of the internet such that we could do better control. So there will be two more bits we'll have to talk about, but it will be at the end of chapter 3. And that takes us to, the urgent data pointer. So this is actually working with the urgent bit. When the urgent bit is on, then the transport layer of TCP is going to look into this pointer and then grab whatever the data that's here indicated by the pointer. So this data here will be extracted and passed out as quick as possible. And receive window here. Yeah, this is the window size for the flow control. Okay. If you recall earlier in the overview, we say flow control is for the receiver to tell the sender, hey, slow down or speed up. And when the slowdown is to be communicated, receive window here will be a small number. If the receiver wants the sender to speed up, the receive window there will be larger. And the last two fields in the header are these. The sequence number as well as the acknowledgement sequence numbers. So these are exactly for the reliable data transfer purpose. But keep in mind, we're now counting the bytes, okay, not packets. TCP sequence number and ACK numbers, these are very important fields. Let me elaborate more here. First, the sequence numbers. So what the sequence number says in the packet header is to tell you this. The byte stream number of the first byte among all the data bytes in the packet. So, but what is the byte stream number? Let me explain. This is the original message, which can be really large, generated by the application layer process. Now, as it's pretty long, right? Each byte can be indicated in sequence in byte stream number. So this is byte 0, byte 1, byte 2, byte 3, byte 4, and so on, so forth. So these numbers, these serial numbers, are the byte stream numbers. So when such a message arrives at the transport layer, the TCP sender is going to break them down into smaller parts. Let's assume that in the first segment, it contains only 3 bytes of the data. So in the header here, the sequence number is going to be what? The byte stream number of the first byte of data, which is 0. For the second packet, in the header sequence number field, what should be the value? It should be the byte stream order of the first byte of all the data, right? So 3 here. Okay, so that's what sequence number meant. And it tells you where the first byte of this data packet is in the original message. So we could track whether all the bytes in the original messages are being transmitted successfully. Second, the acknowledgement number. Now to explain this, let me tell you TCP implements. Just like go back in, cumulative X. So that number there, based on your knowledge of go back in, should indicate what? The last byte of all the data received correctly at the receiver and in sequence. But, well, it's actually not quite. So TCP's acknowledgement number is actually counting 1 byte further. So it's the next byte the receiver is expecting. So that number is the number of the next byte the receiver is expecting. Therefore, it will also be the what? The sequence number of the next data packet coming from the sender. And with that said, many of you will probably guess that TCP's reliable data transfer mechanism is similar to go back in. You are actually correct. So let me borrow the diagram that I've been using to explain the sender side behavior of go back in here. The only difference is just that previously, now each rectangle indicates a packet. But now we are counting bytes instead of packets. So each of these are what? Bytes. So we have green bytes, yellow bytes, blue bytes, and gray bytes. But similarly to go back in, the green bytes are what? The bytes that are already sent and acknowledged. Yellow ones are the bytes sent and not yet acknowledged. Blue bytes are those usable, so if there are more data the application layer process wants to send, we could now turn these blue ones to yellow. So usable but not used. Gray ones, not usable because it's what? Outside of the window size, outside of the window limit. Now, the sender generates a data packet. What's going to be in the sequence number is what? The first byte of the data and the byte stream number of it. And if an acknowledgement is coming back to the sender, acknowledging this packet, the acknowledgement number here is going to indicate what? The byte stream order of the next yellow packet. So this first one here is going to turn green. Yeah, so ACK number here is the first yellow next. And the last bit here is again about TCP's RDT being very similar to go back in. So if you recall, go back in's receiver, when it receives out of order packets, what does it do? It drops all the out of order packets. Now that is actually a wasteful use of network bandwidth, isn't it? So TCP here allows a bit more flexibility. The programmers themselves can decide whether to buffer the out of order packets or to drop them. Now let's exercise what we learned about the TCP sequence numbers and ACK numbers using a simple telnet scenario. The setting is this. We are here at host A. We've already started the terminal and it's connected to the remote machine, host B. So what happened in the telnet is this. When we hit C, a key locally, okay, so user type C, what happened is this. Host A sends a byte, that character C, to the remote machine. Now the remote machine is going to receive this and see what to do with it. Now, because it's a very straightforward character C, not like escape or control C, therefore, what it does is going to be simply echo back the character C to the local host. So host A here will receive the echo C and then display on the local terminal. So once again, host A here has 1 byte to send. Host B here has 1 byte to send. And that's the scenario. Now, the 1 byte of data generated by the telnet process. As soon as it arrives at the transport layer, we're going to add header to it. So sequence number, ACK number being added to it. And the data is simply a character C. Now, when this packet arrives at host B is going to what? Yeah, echo with the same character C. And in the meantime, acknowledge receipt of the data packet earlier. Right? So what will be the sequence number and ACK number will be generating? Well, we send 1 byte of data. What should be the sequence number there? Well, go back here. The ACK number is indicating what is the next sequence number. Yeah, the sender of the ACK packet is expecting. Therefore, sequence number we know should be 79. Now, what should be the ACK number here? Well, ACK number is what? the last byte received and then counting further by 1 byte. What is the last byte received? Yes, 42, because there's only 1 byte. And counting further, yeah, we say ACK43. And this is also host B telling host A, what is the next data byte expected? And therefore we see the next packet coming back from host A, sequence number 42. But host A here is not echoing C anymore. All it needs to do is to what? Acknowledge receiving this packet. Right? So ACK packet needs to be what? Last byte received by host A, which is 79 because there's only 1 byte. And counting further by 1. Therefore, we get 80. So you see, quite obviously, in order to find out what is the next sequence number, look at the packet coming the other direction's ACK number. In order to find out what is the ACK number, look at the packet sequence number coming the other direction. Similarly, sequence number here, look at the ACK. The ACK number, look at the sequence of the last packet coming the other direction. Alright, so that was sequence number being counting bytes. So this is quiz number 17. So let's try exercising byte counting a little bit more. Okay. So what you're seeing on the left is a very simple scenario. Okay. Data is only going from host A to host B. Okay, so you see here, the first packet from host A carries sequence number 42. And there's 7 bytes of data in the packet. Therefore, host B sends back an acknowledgement, and that acknowledgement should be indicating the byte order number, the byte stream number of the last byte plus 1. Okay, meaning what is the next byte host B will be expecting. So if the starting byte is 42 and there are 7 bytes, what is the last byte's number? That should be 42 plus 7 subtracting 1, right? And therefore the ACK should be exactly 42 plus the size of the data in the packet, 49. Similarly, when host A is sending the second data, the ACK coming from host B is saying that I'm expecting 49. Therefore, the first byte that's going out should be exactly 49 if this is a new data. Okay, and the data is 3 bytes there. Therefore, the second ACK going back to host A should be 49 plus 3. Good. Now, the question is actually on the right. Okay. Again, a pair of hosts A and host B. What we know is that in TCP, data can go both directions. So it's not as straightforward as the scenario on the left. Data only go from A to B. Now, host A and host B on the right can send data both ways. All right. So you see in the first packet, host A is sending a data. In the meantime, acknowledging something. Okay. So that packet starts from the byte stream number 42. Okay. And the data size is 10 bytes. What should be the ACK number in the packet coming back from host B? Now, of course, we assume there's no bit error, no packet loss here. All right, so the next packet there coming back from B to A is definitely acknowledging receiving the data, the 10 bytes of data. Okay, so what should be the ACK number there? And that should be B. Okay. And host B here is also sending data, in the meantime sending back ACK. So what should be the sequence number, the A there? Okay. And there's only 1 byte of data host B is sending back. Similarly, host A generates more data and sending back this direction to host B. And that packet not only ACK the data coming from host B, but there are more being sent, 40 bytes of them. Okay, so what should be the sequence number and the ACK number in the third packet? And what should be the sequence number and the ACK number in the fourth packet? So quiz 17 is asking you to tell the value of A, B, C, D, E, F, the ACK numbers and the sequence numbers in the second, third, and the fourth packet in the scenario on the right. Alright, so this should be relatively easy. It's just allowing you to exercise TCP being bidirectional and how we count the data by bytes, no longer by packets. So you have 3 minutes to work on this. So let's go ahead and start. Actually, Polly doesn't know the answer for A, B, C, D, E, F yet, so I'll be working on it in the meantime. Alright, so we do have one team. Okay, A79, B52, C52, D80, E80, F. Okay, that sounds correct because that agrees with what Polly had. So Kevin, or team 1, team 4. And I think Gao is team 10, I think. There we go. Good. Okay, team 5, Jiaze. Yeah, the same. Good. Yeah, this isn't so hard, is it? It's just you know, you need to check, you know, the numbers a bit more carefully, right? So what I did is this. I actually find out what is sequence number A first. And because A should be what? Exactly the ACK number of the previous packet coming the other direction. So A is obviously 79. And B here should be the sum of the sequence number and the size of data in the previous packet. So B is 42 plus 10. And therefore, what? C should equal to B. Yeah. And therefore, D should equal to, what was that? A plus 1. And so on and so forth. Yeah, team 2 also gets it. Very good. So, C and team 5 and team 2. You're good as well. And by the way, Gao, team 10 is also good. All right, so that should not be too hard. It's a bit confusing at the beginning. You just need to exercise it a couple more times. All right, so let's move on to the next topic. Yeah, in reliable data transfer mechanisms, we keep saying that we need a timer. When the timer times out, we retransmit the packet. And this is necessary because in case the packet is lost, the only way to figure it out is to wait. When it's long enough, you lose the patience, then you retransmit the packet. But how long do you wait? How long is waiting long enough? Yeah, in TCP, being a real mechanism that we need to implement, the timeout interval, the decision of that needs to be very concrete and very clear. And so that it's not too short and not too long. And let me describe with the fundamentals of TCP packet format. TCP being bidirectional, and we're actually counting bytes instead of packets. So with these out of the way, we can now come back to talk about the reliable data transfer mechanism implemented in TCP. Before pollys shows you the finite state machine of TCP's RDT, let's define this thing first. It's called the timeout interval or timeout value. Now, TCP being implementing a reliable data transfer protocol, it needs to also define this thing clearly. What is that? If you recall back and go back in, we said that after packet gets transmitted, we start a timer. That timer is going to tick, tick, tick. If an ACK does not come back before that timer expires or that timer times out, then what? We retransmit packet. So this timer there is to allow us to decide whether a packet is lost inside the network. So it's part of the RDT mechanism that is very critical. And that interval determines how long the retransmission is going to go. And that influences the performance of the reliable data transfer. We know already in some earlier example, if that timer is set too short, yeah, so packet can sometimes travel the internet a bit longer than usual. If that timer is too short and expires, then retransmission right before ACK arrives back, then this retransmission there is unnecessary and premature. Okay? That is not a good thing in terms of bandwidth consumption. So, not good. If that timer is too long, yeah, the intuition also says it's going to take a long time for the sender to discover there's a packet loss and try to recover from it. So you see that the user experience with sending data over this connection is not going to be good. Okay, so slow reaction to packet losses. Either case, not good. So how do we find a balance? How do we set or how do we estimate the timeout interval? You see, it's not that far-fetched. You heard pollys saying this already. The interval should at least cover what? Time data travel to the receiver and the ACK coming back from the receiver. And we know this is called what? The round trip time. But you also heard pollys saying that sometimes it takes longer for the data or ACK packet to travel the internet. Therefore, the timeout interval there should be set to cover longer than most of the round trip time that the pair of sender-receiver might experience. And that is the idea behind how TCP estimates the timeout interval. And you see also, in TCP, it needs to observe the round trip time repeatedly in between the pair of sender and receiver. Okay. And this is exactly how it's done. Okay. For a pair of data goes out and the ACK come back, it calculates the time differences between receiving of ACK to the sending of data, and we get a simple RTT. Now, there will be a lot of these simple RTT for each data and ACK pair. But we will ignore the data ACK pairs due to retransmission. So some of these data might get lost and therefore they get retransmitted. When we receive an ACK for such a data, it could be a bit confusing, right? What is the right data sending time to subtract in order to be sure that this is really estimating just the round trip time and not covering a premature timeout, things like that. And we get lots of these sample RTTs, and they could vary quite a bit. So you see that it's actually not good to use the sample RTT as the timeout interval for the next packet. Not good. So what TCP does next is this, to get a smoother estimation of the round trip time. Okay? And that is done by taking the average of multiple recent sample RTTs. So what Polly brings up here is essentially the line of code in TCP's implementation, estimating the smoothed RTT. So the estimated RTT, this variable is to refer to the smoothed RTT. Now the smooth RTT next is going to be the smooth RTT now, and take a weighted sum of that to the current sample of RTT. Okay, so current smooth RTT, and take the weighted sum of that to the current sample RTT. Okay, so we're taking the history into consideration, that's why it's called the moving average. And we're using a special factor alpha here, so it's a weighted moving average as well. Now the reason that it's called exponential is because of this, right? So the whole thing is the current, okay, smooth RTT. Now this whole thing is going to be used as what? The first term of the next estimation. So you see, the current smooth RTT is going to be weighted what? 1 minus alpha, actually, 2 times. So the current estimated RTT 2 rounds later will weight exponentially less. Okay? 3 times 3 exponents less, 4, and so on and so forth. So the past sample, the influence of it will decrease exponentially fast. Oh, and by the way, alpha is only 0.125. That is because, we don't want to weigh too much on the instantaneous RTT, because otherwise it will be what? Also fluctuating, okay? Not exactly smooth. And here shows, the instantaneous RTT and the estimated RTT, the smoothed estimation, how they look like relatively. And this is actually actual measurement between UMass and Euler-Com again. Okay. So the blue one that fluctuates more, like these. These are the instantaneous RTT, the sample RTT. The pink one then is the estimated RTT, the smoothed, the average RTT over time. So you see that although the blue one fluctuates a lot, but the pink one, relatively smooth. And you see also, generally as time goes along, the round trip time tends to be longer. And so you see the pink here, the smoothed average RTT is tracking the increase of the RTT relatively well. But be careful here. The estimated RTT is definitely not quite yet the timeout interval used by the TCP. Because if you do, you see these guys here, the round trip time is actually way longer than the timeout interval. So for all these guys, you will get premature timeouts. So the estimated RTT there is certainly not covering most of the round trip time observations. So there's more. Therefore, in TCP, the exact timeout interval is in fact the estimated RTT, the smooth average, plus a safety margin. Okay? The safety margin there should cover the variation of these RTTs, and hopefully a good portion of the variations. So if we have a large variation in the estimated RTT, we should use a large safety margin. Okay? So this safety margin is captured by another variable called the deviation of RTT, DEV-RTT there. And we are again borrowing this technique called the exponential weighted smooth or moving average. Okay, so EWMA again, okay, to estimate the deviation of round trip time. What is the instantaneous deviation? Well, it will be what? The current instantaneous RTT subtracting the current smooth RTT. So this is the deviation of the RTT to the average. Okay. And so current sample weighted sum by the history of the deviation will be the next deviation of RTT. Okay. Now in this part, the alpha is set typically to 0.25. Okay. This is again, we don't want to weigh too much on the instantaneous RTT, but the variation is relatively less fluctuating than the instantaneous RTT. So this is actually higher than 0.125. And most of the exact values we're setting for TCP are actually the result of estimation, measurement, and then deriving the best alpha and best beta. So people just borrow from other people's study and using these parameters accordingly. So finally, the timeout interval there is the estimated RTT plus 4 times the deviation of RTT. Okay, so safety margin covers the deviation, okay, the variations of RTTs. But the timeout interval is actually what? The average plus 4 times the deviation. Oh, what does that mean? So 4 here, seemingly randomly chosen, but if you recall statistics, okay, your first lesson of statistics, there's this thing called the what? Normal distribution. Yeah. In order to cover 99% of the samples, you have to add, okay, average to 3 times the standard deviation. So adding 4 times standard deviation is to cover way more than 99%. Okay, so this is also saying what? TCP is setting the timeout interval such that it covers 99.9 something% of the RTTs. So we are very safe. Using this timeout interval, only a very small portion of the packets, the timers, will time out prematurely. That will save us a lot of what? Bandwidth for unnecessary retransmission. Therefore, in TCP, the timeout interval is the estimated RTT plus a safety margin. So estimated RTT is the what? The average. Okay, so that's actually the same recording being repeated again. So yep, that is all for today. And if you have further questions you want to ask, feel free to type it up. Otherwise, I'll see you tomorrow. And that will be 10:20 tomorrow. Good, so you're free to go. And sure, if you want to finish quiz 17, feel free to do that now. Good. And the time is up, so let me end the stream right here.